Right, so let's continue, okay, from where we were, okay, and yeah, you still water. And one reminder, tomorrow there will be a test on organic chem. So make sure you review naming of compounds, remember that revision sheet, right? And then some reactions, okay, of alkene and alkene. You know alkene undergoes substitution. Alkene undergoes addition, okay, and know the requirement. Which of those reactions require UV light? Is it alkane substitution or alkene addition? Alkane substitution. So that will be on the test. I can already tell you that. Okay, yeah, so if you don't revise for that that's on you. Okay, so next, last time we stopped here. We looked at some simple molecular substance and giant covalent structures. Okay, so I think the projector in this class is much better in quality. So you can see that there are many different giant covalent structures, including diamond and graphite. So how is the structure of graphite different from that of diamond?
Layers.
Sorry, I got confused with the classroom.
Right. Okay. And yeah. So make sure like this is the new class. Okay. 505. So for graphite, how are the carbons connected?
Layers.
Yeah, they form layers, but on each layer,
Hexagon.
they form hexagons. Yeah, you see, you have something that looks like this. So you have one graphite layer, and then another graphite layer here. Right. So this is another graphite layer. So you're right. They have a layered structure. Okay, in graphite. And most importantly, in diamond, each carbon you see is bonded to 4 other carbons. But in graphite, how many other carbons is each carbon bonded to only?
2.
Oh, don't look at those at the edge because I haven't drawn the complete structure here. We can only focus on these ones. So how many? 3. Yeah. Okay. So remember what I said, because the carbons, you cannot possibly draw the entire graphite structure. It's too extensive, too large. So you might want to just focus on these ones in the center. Okay? So let me just put this in here. From this carbon, each carbon is bonded to 4 other carbons. And from this carbon, each carbon is bonded to 3 other carbons. Right, so to 3 other carbon atoms. Which means, how many electrons does it have left in the outermost shell? Carbon is group 4. That means it should have 4 outermost shell electrons. So after forming bonds with 4 carbons, are there any electrons left? No, not in diamond. But in graphite, how many electrons is left? 1. So therefore, graphite, is it a conductor or insulator? Conductor. Okay, so can you put down some chemistry of carbon here? So carbon it has atomic number 6. And so the electron arrangement, what is it? What is something with 6 electrons? What is the electron arrangement of something with 6 electrons? Electron arrangement means how you put electrons in shells. How are you going to put 6 electrons in carbon? Do you put them all in the first shell? 2, 4, 2, 4. Okay, so that means in the outermost shell there are 4 electrons. So this is carbon with 1, 2, 3, 4. Okay, so there are 4 outermost shell electrons. So in diamond, I hope this is not too loud. Okay, so in diamond, all 4 of the outermost shell electrons they are used. So there are none left. Okay, and this means diamond has no delocalized sea of electrons. So you may want to jot this important point down. So it has no electron for delocalization because all 4 of the electrons are used in bonding. Okay, because 4 of 4 electrons are used for bonding, in bonding. But then in graphite, it has 1 electron for delocalization from each carbon. Because you see, knowing that carbon forming just 3 bonds, okay, it will have used only 3 of the 4 electrons in bonding, right? Yeah, makes sense. So this explains why the property of diamond and graphite are so different. Okay, how different? Diamond is an insulator. because there are no electrons for the localization. And graphite is a conductor because each of the carbon will throw out an electron, you see? So it will throw out an electron for the localization. So making it conductive. Okay, so that's graphite. And do you all know other examples of giant covalent structures other than diamond and graphite? Si and SiO2, right? Si and SiO2. So actually, I don't need this, box in here. So let me just throw this away. So we have Si and SiO2. And actually, the diagram for Si and SiO2, they are very similar. Okay, so I'll just draw it in here first. 1, 2, 3, 4. Like, just like in diamond, you see they are connected to 4 other partners. Okay, each of them. But unlike in diamond, which is made of pure carbon, okay, this is made of silicon. Okay, so this is made from silicon. So each of these are now Si instead of C atoms. But structurally, it is the same thing as diamond, you see. Can you see these two diagrams? They are mostly identical. Okay. What about SiO2? SiO2 will be built on, actually I can just copy this over. SiO2 structure will be built on that of Si. So we put SiO2 here. And then you will find additional oxygen here in between any two Si atoms. So this is what SiO2 looks like. So SiO2 is known by the other names. Do you know the other names of SiO2 silicon dioxide? Quartz, yes, okay. And it is the same thing found in sand and glass. So this is why sand can scratch your phone screen. Because your phone is made from glass, that's the screen. And sand is made from the same material, meaning they have the same hardness. So you can scratch your phone, not with knife, but with glass, with sand, okay? So know the other names of SiO2, quartz, but quartz is a mineral. And then we have silicon dioxide. Yeah, they mean the same thing. And this is found in glass and sand. Right. Quartz is in glass. Yes, okay, and in sand. Okay. So this is giant covalent structure. So why did I go through these covalent substances when we talk about microscopic world 2? That's because in the second half of microscopic world 2, okay, remember we have a test tomorrow. Okay, almost in okay. So I'm really worried that you will say, oh, I didn't know like tomorrow, okay? Yeah, so then the symbol normally Sarah is absent. Okay, absent. Yeah. So here, what about just make sure you remind her as well. Okay? So because yeah. So next up we have intermolecular forces. Yeah, which I'll abbreviate as IMFs from now on. Okay, so intermolecular force, but you should keep calling them intermolecular force on your paper. Okay, yeah, I'm just keeping it simple, keeping it simple. So what are intermolecular forces? Well, in simple molecules, so in simple molecular substances, such as, for example, CO2, H2O, or even C60. Do you know what C60 is? Have you seen this ring before? No. Okay, so this is a form of carbon, which we call fullerene. Okay, let me draw out CO2 for you first. So you know this is CO2. So this is a molecule of CO2. So what are those orange lines? What are those bonds called? Covalent bond. Covalent bond. Okay, so yeah, they are bonds, but you have to be specific in the exam. Okay, and call them covalent bonds. And then between H2Os, okay, between the H and O atoms, you have also covalent bonds. And you should be able to explain why this is a V-shaped molecule when CO2 is a straight-shaped molecule. Now, why is H2O like a V-shaped molecule? Why can't I draw H2O like this?
Two lone pairs.
Because there are two lone pairs. Okay, so if you want to check how many lone pairs it has, so make sure you don't draw H2O like this. You have to draw it like this. But because there are actually two hidden lone pairs, okay, that you did not show. There are two lone pairs on the oxygen. That is, explaining the shape. So what about C60? C60 is even more complicated. But if you know what a football looks like, you know what C60 looks like. So C60 is basically carbon connected in the form of a cage-like structure that resembles football. But you don't have to draw this because even I have a hard time drawing this. So each of these junctions here, at each of these junctions, you will find a carbon. And if you have 60 of them bonded together to form this cage-like structure, we call this a C60 molecule. Okay? So each of these is a molecule, you see? So this is a molecule. This is a molecule. This is also a molecule. So we say in these structures, they are discrete molecules. Okay? So all these examples, why are they called simple molecular substances? So all these are simple molecular substances because they consist of small discrete molecules. Okay, so because they all consist of many small discrete. So discrete meaning separate molecules. Can you see that this molecule is not connected directly to this one? Yeah, so this is why we call them simple molecular substances. But still, actually I think it's better that I draw these in orange. Yeah, so these lines in orange. So you know those bonds, they are still covalent bonds. But between the molecules, are there any covalent bonds? No. Instead, we call those intermolecular forces. Okay, so you will draw these dashed line, okay, on your notes. Make sure you draw that. And then we will draw a key on the side. What does the orange rigid line or solid line and the yellow dotted line represent? The orange line represents strong covalent bonds. Okay, so you have, write this down. Strong covalent bonds. Where do you find this? Is it within a molecule or is it between molecules? Between atoms means within one molecule, right? Yeah, you know this is a molecule. Within this molecule, you see the orange line. But then what about between one H2 molecule and the other? Intermolecular force, okay? And you have to add this adjective in the exam. Don't just call it intermolecular force. Call them weak. We'll call them intermolecular force first, as when the Wells is only one of them. Okay, one of the many intermolecular forces. So write down strong covalent bonds and weak intermolecular force. Where do we find them? Strong covalent bonds is found within a molecule, singular. And weak intermolecular force can be found between molecules. Okay, so this is plural. Okay, so between molecules, you find this here. And within a molecule means you find it here, 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 inside a single molecule. Is that crystal clear? Okay? But yes?
What's C60 used for?
Oh, what's C60 used for? C60 is a semiconductor. Okay, so well, if you ask me what use does a semiconductor have, maybe in electronics. But yeah, this is C60. And the rest you should already know. So I'll put down CO2 here, H2O here, and this is C60. So that means you now know 3 different forms of carbons, okay, which I'll summarize for you here. Okay, so there are 3 forms of carbon. What are the other 2 that you know? What is that very expensive substance that you find in jewelry store made of carbon? Diamond. Okay, so that is one form. What is the other form that you find in pencil? Graphite. And now you know the 3rd form, C60. It is also carbon. Okay, so 3 forms of carbon. Right, we have. So you can put down. Carbon can be either like a simple molecular substance or giant covalent structure. So giant covalent structure. So under simple molecular substance, you have the example C60 only. You don't have any other. Okay? And then under giant covalent structure, you have the 2. You have diamond. If you really must write the formula for diamond is C. Okay? C with infinite number, uncountable number of carbon. And then you have graphite. So graphite is also C. So the difference between them is that in C60, there is a countable You see the number 60. 60 is a countable number, right? Yeah, so there is a countable number of C atoms. Both diamond and graphite, they have an uncountable number of carbon atoms. So that's what makes them giant and simple, you see. So simple and giant, so countable and uncountable. So that's the connection. Okay, so because of this that you call it simple, and because of this that you call it giant. And simple molecular substances and giant covalent substances, which of these have higher boiling point? Giant. Okay, so you have higher melting and boiling point. So this is why diamond and graphite, they are solids. I don't think I need to tell you that they are solids. Okay, but C60 is a liquid. Okay, so this has a lower boiling and melting point. Okay, now let's move on. Okay, so just now when I asked you what is present between molecules, you said van der Waals force. Okay, but unfortunately I have to tell you that van der Waals force is just one of the two possible intermolecular forces. So let's look at them now. So types of intermolecular, before that I should tell you something. Is which of these forces do we break when we melt or boil a simple molecule? Do we break the covalent bond, or do we only have to break the weak intermolecular force when we melt or boil a simple molecular substance? Intermolecular force. Okay. And let me show you how you can remember this. Okay, so which is broken? Okay, strong covalent bonds or weak intermolecular force? Yeah, so strong covalent bonds or weak intermolecular force when we melt or boil a simple molecule. So melt or boil a simple molecular substance. So just ask yourself what you get when you boil water. Do you boil water into hydrogen and oxygen atoms? Never, right? I mean, if that's the case, you better run from the kitchen because a mixture of hydrogen and oxygen is explosive. Okay? And instead, what do you get when you boil water? Steam. And steam is just gaseous water, right? So if I give you a magnifying glass, okay, and ask you to draw what you will see inside a sample of liquid water and inside a sample of steam, what do you show? They are both H2O, right? But what is the difference between the H2O molecules in these two samples? In which state are they farther apart? Gaseous state. And in liquid state, they're just closer together, right? So that means, let me finish this sentence first. A simple molecular substance. So here we look at the example, water. So water, you know, is H2O. It is a simple molecular substance. When we boil water, what do we get? So we have something like this. This is H2O. Okay. So in the liquid state, you see they are pretty close together. And in the gaseous state, they are much further apart. So this is what happens. Okay, so this is what happens when we boil water, right? Okay. So what didn't happen? Okay, so it did not turn into a bunch of H and O atoms. So from this, what can we conclude? Is it only the intermolecular force or the strong covalent bonds that we are breaking when we boil or melt a simple molecular substance? Intermolecular force. Can you see that? Okay, so from this simple everyday life example, you can tell that the covalent bonds, they will not be broken, okay, when you melt or boil a substance. So what is the thing that happened? The intermolecular forces are broken. Okay, so IMFs are broken. And what did not happen? The covalent bonds breaking. Okay, so covalent bonds are broken. So they will not be broken, okay, when you melt or boil the substance. So let me put this down. This will not happen. Okay, so from this, what conclusion can we draw? So the conclusion is that when we melt or boil, a simple molecular substance, only when we melt or boil a simple molecular substance, only the weak intermolecular force and not the strong covalent bonds are broken. Is that clear? Okay? So only the weak intermolecular force and not the strong covalent bonds are broken. As such, does it take a lot of energy or just very little energy to melt all simple molecular substances as a whole? Little, because these are weak. That's what weak mean. You don't need much force, okay? You don't need much heat to break them, okay? So not strong covalent bonds need to be broken. So therefore, the next point here that we'll add is, because these are weak, therefore it will take little heat to break. So take little heat to break, resulting in them having low melting and boiling point. Makes sense, right? Yeah, okay. So now, over here on the opposite side of the page, okay, we'll look at two different types of intermolecular force, which you need to remember. In Form 4, you just call it intermolecular force, right? Now, we have two different types to remember. So two types of intermolecular forces, okay, and they are, number one, Van der Waals force, okay, so you want to write down Van der Waals. So it's named after the scientist who discovered it, okay, Johannes Van der Waals. So this is found by Van der Waals. So we have Van der Waals. Actually, you spell his name correctly. You don't want others to spell your name wrong. Okay, so you spell his name correctly. So Van der Waals force, which I'll just call it VDW from this point onward. The second type is known as hydrogen bond. So if you are also doing biology, you may have heard of this. There's hydrogen bond in many molecules, including proteins, including DNA, okay? You know DNA is like a zipper, right? Yeah, so how do they zip together? Through hydrogen bond. Okay, we'll look at this very amazing type of intermolecular force in this chapter. So, hydrolysis has nothing to do with hydrogen bond. Okay, a hydrogen bond is just like some kind of connection that holds atoms or molecules together. Like I said, in DNA, okay, or in protein, okay. You know, in protein there are these shapes, okay, the alpha helix, okay. So they connect by a hydrogen bond, okay. So this is what caused them to become this spring-like structure, okay. So this is protein. For example, cotton. Okay, cotton looks like this. This is why it's so stretchy, because when you stretch it, it will deform, but as soon as you let go, it will bounce right back due to those forces called hydrogen bond. There's hydrogen bond in cotton, which makes it stretchy. Okay? Yeah, but we will not be digging too much into the biology aspect. Okay, let's just focus on the chemistry aspect. What's the difference between these two types of intermolecular forces? Why do you have to differentiate between them? That's because Van der Waals force is found in all molecules. So the keyword here is all. Molecules can be polar or non-polar. And Van der Waals force is like the type of intermolecular force that's found in all kinds of molecules. It doesn't differentiate between the polars and the non-polar. Everybody will have this. Every molecule will have this intermolecular force. Okay? So found in all molecules, write down both polar and non-polar. Yeah. What about hydrogen bond? Hydrogen bond is a bit tricky. Okay, so it is found only in very polar molecules. So what are some very polar molecules? Well, we say these molecules with three types of bonds that you need to remember: HN, HO, or HF bonds. Okay, so HN or HO or HF bonds. Why are these three atoms so special, N, O, and F? By the way, you can remember them as north, NOS. Just put them together, north, remember north. Where are these atoms located on the periodic table? Do you know which corner on the periodic table are these atoms found?
Right.
Top right, top right. And do you remember the electronegativity trend from last lesson? How does electronegativity change across the period and down? When you go from left to right, it becomes larger, yes, okay? So you remember that electronegativity increases across the period, but it decreases down the group, right? Yeah, oh, yeah, you will answer last lesson. Make sure you refer to the video. Yeah, I made those videos for you, so you have no excuse to say, oh, I was not here, okay? Yeah, it is always there, okay, on YouTube. If you have time, you can always watch it. So that's not an excuse. Okay? So electronegativity increases across the period, which means these three atoms, when they bond to hydrogen, what will happen to hydrogen? Let's take HF as an example. F is a very greedy atom. I like to think of electronegativity as like greediness for electrons. How much the atom wants to keep the electron to itself. When hydrogen is unfortunate to form a bond with fluorine, it will have almost all the electrons taken away from fluorine. You can think of this as like a book sharing example. So this is a very peaceful guy, and then here there is a very aggressive guy. Okay, so this aggressive guy is pulling the book all the way to him. Okay, so it's keeping the book to itself. So this is the book. The book is analogous to the shared pair of electrons. So you have the shared pair of electrons. Okay, so the book is analogous to the shared pair of electrons. And you see this is a very aggressive atom, F. Okay, and this is a less aggressive atom, H. Okay, so this will make for a very positive hydrogen and a very negative fluorine. Okay, so you have hydrogen bond. We'll get to that shortly. But any question about the two types of intermolecular forces? No, we will look at the origin of these two forces now. Starting with van der Waals force. Okay, so we'll put that in the middle. So the origin of intermolecular forces. So number one, we have van der Waals force. Let's take a look at two molecules, and you tell me if there are attraction between the molecules, okay, and why. So we have HCl molecule. So let me give you an introduction sentence here. Van der Waals force is found in polar and non-polar molecules. Let's just take HCl and ClCl as an example. Do you all remember why would we consider HCl as a polar bond and ClCl as a non-polar bond?
Zero.
We need to calculate something called electronegativity difference, right? So if two atoms, they are on different sides of the periodic table, so remember to refer to this, which I will give you always in the exam if I ask a question on this. Can you see H and Cl? When you find the difference in the electronegativity between these two atoms, what is it? 0.9, okay? And 0.9, if you remember, is larger than 0.4, which makes it a polar bond, okay? So therefore, before we answer any question on whether a molecule is polar or not, or a bond is polar or not, we need to first ask for the electronegativity. Then we calculate the difference and see if it's larger than or smaller than 0.4. Then we will know if a bond is polar. So once you know that a bond is polar, what does a polar bond mean? It means there is an uneven sharing of electrons. And a non-polar bond means there is an even sharing. So you see, do you see that the electrons, they are distorted towards one side in HCl? Because Cl has a higher electronegativity. Remember, electronegativity means greediness for electrons. So Cl keeps most of the electrons to himself. But in the case of ClCl, the two atoms, they attract the electron equally well, right? So this is why there is no distortion in the electron cloud in ClCl. So when you look at the two HCl molecules, can you tell me which end of the HCl molecule has a positive charge? Which end of the HCl molecule has a negative charge? H has a positive charge because it has fewer electrons than usual, right? Yeah, you can think of this Cl, the electrons around Cl as how much electron that should be around an atom usually. But can you see that this H has less than usual the amount of electrons? As a result of that, we say it has a delta positive charge, this hydrogen. Remember, delta positive means electron poor. It's lacking in electron. The other end, just look at this Cl. It has more electron than usual, right? This is how much electron that should be around an atom usually, okay? And this is how much electron this chlorine is having. You see it has more than usual. Having more than usual meaning it has a delta negative charge. By the way, this sign is pronounced as delta. Delta means slightly, just a little bit. Okay, just a little bit of positive charge. And this is just a little bit of negative charge. Delta negative means electron rich. And for those of you who know a bit of physics, you don't need to do physics to understand this. What is the nature of force between two oppositely charged like objects? Is it attraction or is it repulsion between something positive and something negative? Attraction. So this is why if I have one HCl molecule over here on the left, and I have another HCl molecule over here on the right, and I put them next to one another, there is attraction between the molecules. So this is attraction. Just because opposite attracts, okay? This is a simple lesson. So help me review this part. Okay, so we covered a few things today. What does simple molecular substance mean? And point number 2 is that we have made a class after school today. So make sure you all attend. Okay. Then you can refer to the video. Okay, but for those of you who do not have anything to do after school, please come. Yeah, this venue, or maybe you can go to that venue. I think the classroom there will be empty later. Okay? Yes. You have another event. Then you can do it. But some students can still make it, right? Or all of you have something to do. Some of you can make it. Yeah, and then for those of you who can come in person. For those of you who cannot, refer to the video. Okay? Yeah, so I'll see you after school. Okay.
It's okay if you don't want